Hello everyone. I'm Daniel. I'm a new assistant teaching professor here in the computer science department at CMU. And I'd like to tell you a little bit about my research interests. So predominantly, I'm interested in parallel algorithms and concurrent algorithms, and specifically shared memory parallel programming. So that is implementing algorithms and programs that use multiple processors that are all sharing the same data in memory. And even more so than that, I'm particularly interested in making tools and libraries that make parallel programming easier for non-experts, since traditionally parallel programming has been an area that is filled with pitfalls and is very, very difficult to do without writing bugs. So I like making tools that make this more accessible to beginners and non-experts. So I want to just give you an example problem to demonstrate like some of the perils of parallel computing and concurrent algorithms. So let's say we have our favorite data structure, a linked list, and we just want to read that linked list. So let's say we have a thread, it reads the head pointer, reads the node A, and it now wants to walk down the linked list and follow the nodes. So it reads the next pointer inside the node, sees that points to this node over here. And now, since we're running a parallel program here, let's say that at this point the thread decides to go to sleep. Maybe the operating system needed that processor for something else, and another thread pops in and decides that it wants to do something. Now, in particular, let's say this thread decides that it really doesn't like B, so it decides to delete B out of the linked list. So it does the standard algorithm for deleting from a linked list. It swings the next pointer of A over to C, the node which comes after B, and then deletes B. Okay, so B is deleted, the node is gone, and its memory is freed back to the operating system to do whatever it wants. Thread 2 is now very happy having deleted B, and it's going to go away satisfied with what it's done. But now thread 1 wakes up from its nap and says, "Ooh, I'm really excited to read that node that I was about to read." Unfortunately, that node is gone, and this will cause your code to crash, most likely with a seg fault or a similar kind of error. So this is not good. How do we actually solve this problem? This is a huge and well-studied area, and there's many approaches that you can take. I'll go through a couple ideas here and contrast them by two things. One is how easy they are to use, and the other is the performance you can expect when using this technique. If you've taken any class on parallel computing, you may be aware of locks or mutual exclusion. This is like the most fundamental and simple technique to prevent concurrency bugs. Unfortunately, locks, while preventing concurrency bugs very effectively, also are a huge hindrance to performance because they essentially prevent concurrency bugs by outright preventing concurrency entirely. They simply stop two pieces of code from executing on the same data at the same time. So if you have many processes that want to operate on the same data at the same time, using locks will typically completely destroy your scalability and ruin the performance of your code. So on the other hand, researchers have developed many fancy techniques. Some of them are hazard pointers or RCU, read, copy, update. RCU is used extensively inside the Linux kernel as its primary mechanism for managing memory that is accessed concurrently. Unfortunately, these techniques, while they're very high performance, are very difficult to use correctly. To implement them into your code, the programmer has to substantially sometimes modify the algorithm and change how things happen. And any slight mistake in those modifications, putting something in the wrong order or forgetting to do a change, will simply lead to your code being incorrect and introduce very subtle and hard to find bugs. So this is really it's an expert only technique. So the kind of work I love to do is writing tools that try to get the best of both worlds. So in my work, joint with Professor Guy Blalock and Hao Wei, we developed a library for concurrent memory management that allows you to get the performance of techniques like hazard pointers and RCU, but the ease of use of simpler, more beginner-friendly techniques. And just to drive the point home, I want to just demonstrate to you that it really is easier to use. I have here some code. This is C++ code for finding a value in a linked list. On the left is the code using hazard pointers. On the right is the code using our library. As you can see, the code on the right is fewer than half as many lines of code and substantially simpler at that. The code on the right is more or less the same code you would write if you were searching a single-threaded linked list in which you weren't concerned with concurrency at all. But it entirely prevents the memory reclamation bugs that you would get if you weren't careful. The code on the left, on the other hand, has all sorts of confusing and strange pitfalls in it. If you forget any of these lines of code or you put them in the wrong order, this code won't work. It will have bugs in it which may be very hard to locate and debug. So on the other hand, our library on the right, it has performance that is just as good. You don't lose any of your scalability or speed by using the code on the right. So you get to reap the performance benefits without needing to write insanely tricky, expert-only level code. So that's the kind of stuff that I enjoy working on. If you're interested in this sort of thing, I'd love to talk to you. So thank you very much.